Hi students, it's Dr. Marks, and we are talking about hypothesis testing. Specifically, we're going to take a look at doing hypothesis tests for differences in means. I'm dividing this lecture into two parts so that we can bite off slightly smaller chunks. So let's get started. Now, if you remember in the last lecture, we learned how to set up the hypothesis test, right? Remember the null hypothesis and the alternative hypothesis? And we did that for both one and two-tailed tests. Remember, that was based on whether we had a directional hypothesis. If we did, it was a one-tailed test. If we didn't, it was a two-tailed test. But we didn't actually conduct the tests. We just talked about how to set them up and what we were trying to do. We're going to do the actual tests in this lecture. So this lecture is going to be, or part 1 and 2 together, is going to be about doing the actual hypothesis tests. Now remember, we're looking at just one specific thing, and that's the case of comparisons of sample means. I'll be explaining to you later that there's other things that we could test, but once you understand how to do it with one statistic, it becomes really, really easy. You can do lots of different tests. We're going to be looking at a comparison of sample means when we have a single sample. So something like a sample of males versus a sample of females, where we just have one sample from each. But first, I want to offer you an important reminder, and that is we need to be careful what we can conclude from means. Now, our hypothesis tests on means is a really good place to start. It's going to help us learn if mean 1 is significantly different from mean 2. And by that, we mean statistically significant. So maybe means for males, is it statistically different from the means for females? Is it different in a way that's not simply due to chance? So we might conclude that they are different. Maybe we have that the mean for males is higher than the mean for females, but this can also be misleading. And the reason that it can be misleading is that we have to be careful about inferring causality. Now, guys, you remember our old friend causality, where we're saying something causes something else. We have to be careful about inferring causality when we're simply looking at tests for differences in means. Let me offer you an example to illustrate. Let's say we're dealing with data on smokers and non-smokers having to do with mean age at death. We see that smokers have a mean age at death for our sample of 71.3 years, but non-smokers have a mean age at death for their sample of 76.8. So we all agreed from looking at this, it looks like smokers have a shorter mean lifespan, right? That non-smokers live longer than smokers. All right. But we have to ask ourselves, is this due to chance? Well, it certainly looks compelling, but is it due to chance? That will tell us if this is a statistically significant difference in means. So let's assume that we conduct a hypothesis test and we find that the result is statistically significant, that it's not simply due to chance. We would be able to conclude then that this 5.5-year difference isn't due to chance, but can we conclude that this 5.5-year difference is due to smoking? So we can say that the two samples have a different mean and it's not due to chance, but can we say it's specifically due to smoking? Well, the answer is no. We cannot claim a causal relationship from this. We can say, look, we've got a significant result here, but we can't say it's literally because it's due to smoking. Why can't we have a causal relationship here? Why can't we make that claim? Well, the reason is that there could be other reasons that we're not controlling for. There might be other variables that might cause smokers to die on average earlier than non-smokers. For example, what if our sample of smokers gets less exercise? And what if our smokers eat less healthy? And what if our smokers weigh more? What about things like family medical history, use of drugs, right? You get the idea. There are other confounding factors. And right now, all I'm controlling for is, are you a smoker or are you not a smoker? So I can see if the means are significantly different, but I can't say, look, the reason they're different is because of smoking versus not smoking. We are not holding what we say in economics, all else constant. And you're going to hear that phrase over and over again, or you might hear me say ceteris paribus. So if I really want to say that smoking's the reason, then I need to hold all these other variables constant. I need to have an environment of ceteris paribus. So hopefully you understand what I'm trying to drive home. That if I really want to have a causal story, that it's because of smoking, I need to control for these other factors. Now, if we have large samples, that helps us to control for these other factors. You can imagine if I have super large samples, then my samples will look similar enough. So when I have large enough samples, then maybe this will solve some of this heterogeneity where my sample of smokers and my sample of non-smokers would be really very similar in all these ways. Okay, well, maybe if my samples are large enough. Or we could run what we call a controlled experiment, right? So think about how you might run a controlled experiment for this. Well, I would probably want to recruit, let's say, all males. I want everyone to be the same gender, and I want them to be similar ages, and I want them to have the same diet. So I need to give them a diet to follow, and I want them to have the same exercise routine, and I want to rule out people with, any family history of illnesses, etc. You get the idea. But then I have to have half of them smoke for, let's say, 30 years, and then I've got a controlled experiment. Well, you get the idea what I'm trying to drive home. Clearly, this would be unethical. Nobody's going to fund this research. My university would laugh if I even proposed this, right? Because we have to go through this board who will decide, is this research okay to conduct? And this would clearly not be okay to conduct, but you get the idea. A controlled experiment can try to help us understand if there's a causal relationship because I've removed all those other potentially confounding factors. Now, another option is that we could use regression analysis, and we will be learning regression analysis later in this class, and some of you may have done some already. Regression analysis is cool because we're going to control for all these other variables as much as we can to try to identify a causal relationship. But bottom line, when we're comparing means in our hypotheses tests, we can't conclude there's a causal story. But it is a nice thing to do because it might help confirm that there is something of interest. So when you're doing some kind of research, it might be a good place to start. Look, is there a statistically significant difference? If there's not, maybe that tells you something. If there is, that might indicate, okay, there could be something more to learn here. This could be kind of interesting. All right. Let's continue on. Hopefully you understand my point. Do not infer a causal story when you cannot do that, right? And you've heard me say that before. Now, let's revisit this idea of confidence intervals because we've used confidence intervals, but what you're going to see in a second is that I'm kind of tie it a little bit to this idea of hypothesis testing. So let's use another example. We're looking at health insurance, and we want to know if health insurance leads to better health. In other words, are insured people healthier than uninsured people? So you see here my data set. I've got husbands and I've got wives, and we have two treatments, right? Some people have some health insurance and others have no health insurance. So we've collected a health index rating. You're in one of two treatments, and either you're a husband or a wife. So we've got our mean health index, right? So for husbands with some insurance, our mean health index is 4.01. But for wives with some health insurance, it's 4.02. You get the idea. Now, let's take a look at this upper right cell. We're looking at wives with some health insurance. Remember, we've got our mean of 4.02, but you see below it that number 0.92 in the brackets. So what exactly is that number, and how can we use that number to learn more? Well, it turns out that that number is our standard error, right? We've talked about standard error before. But it's a really abstract concept. I understand it's hard to get your brain around. So, our standard error is a measure of how precisely the sample mean is going to measure the population mean. How good of a job did we do? How reflective is our sample mean in terms of telling us something about our population mean? So, before we go down this rabbit hole, let's just review the idea. So, our standard error quantifies how precisely you know the true mean of the population. Remember, we're collecting a sample and we're trying to infer something about the true mean of that population. But I don't know the mean of the population, right? I can't possibly get this health index rating measure for all wives in the United States that have some health insurance or no health insurance, right? So I'm working with a sample. So our standard error gives us an estimate of the precision of the sample mean. How good of a job does it do for us, right? So this standard error is basically telling us the standard difference we might see between mu. Let's remember what mu is. Mu, that's a symbol we use for our population mean, and x bar, which is our sample mean. So how much difference are we going to see between mu, our population mean, and x bar, our sample mean? How much difference are we going to see between them that is simply due to chance? So the standard error is telling us how much of this difference is due to chance. So let's think about it. Do I want a big standard error or a small standard error? Well, if the standard error is telling us how much of this difference is due to chance, right, then I want it to be only a little bit. I want there to be as small of a chance as possible that this difference is simply due to chance, right? So what that tells us is that a lower standard error means more precision, right? Lower standard errors are good. Big standard errors, we don't want that. That's bad, right? So going back to our data here, our mean for wives in terms of their health index who have some health insurance is 4.02, and I've got a standard error of 0.92. Now remember, we have everything we need to create a confidence interval. Let's remind ourselves about our confidence interval. All right, remember a confidence interval is calculated as x bar, that's our sample mean, right? Plus or minus 1.96, right? We're at the 95% confidence, 1.96 multiplied by our standard error. Remember that 1.96 measure came from our desire to be 95% confident, right, from our t-distribution, which converges to that normal distribution. So if you don't know what I'm talking about here, you need to go revisit the lecture on confidence intervals because this is a calculation we should be familiar with. So I'm just going to plug in what we know. I'm going to plug in 4.02 for x bar, and we have 0.92 for our standard error, right? Just like that. So just plugged in our values. And now I can say that we are 95% confident that our population mean falls in between 2.22 and 5.82. Now remember, why do we like smaller standard errors? Let's remind ourselves, if my standard error goes down, what happens to that interval? Do you remember? Can you tell from the equation? Remember, smaller standard error, that interval is going to shrink. We have more precision, right? So it means that I have a lower margin of error. Okay, so we've calculated a confidence interval around the mean, right? Given the level of confidence that we want and given our standard error. Now let's do the same thing and find the 95% confidence interval for wives with no health insurance, right? The other treatments. And we're going to ignore husbands in this analysis that we're doing right here. We're just focusing on wives. All right, so I'm going to give you a second and I want you to practice. You calculate the 95% confidence interval, given that you know the mean and you know the standard error. So I'm going to pause here just for a second. All right, if you need more time, hit the pause button on this recording so we can roll on. Hopefully you got that we are 95% confident that the population mean falls in between 1.64 and 5.6, right? So now we have a confidence interval for both of the means for wives, when we have some insurance and when we have no insurance. Let's take this a step further. Let's say that we want to look at the difference, right? We had a mean of 4.02 in terms of the health index rating for wives when they have insurance, and it was 3.62 when they didn't have any insurance. So if I calculate that difference, I get 3.9 with a standard error of 0.04. All right. So I'm comparing wives who are insured versus wives who are uninsured, right? So make sure you understand where I got that 0.39. I just took the difference in the means, 0.39. Hopefully I've not made any error there. And we want to know, is this difference due to chance? In other words, is this a real difference or is this just by chance? Which means, this is not statistically significant. So basically, I need to determine if this is a statistically significant difference. All right, well, here's where a hypothesis test can help me. So how does this relate to our hypothesis test? Well, first, let's assume a two-tailed test for now. I know that might not be the most appropriate, but it's just going to be a little easier for illustration. Maybe I want a one-tailed test here because maybe I'm thinking that people with insurance have a higher health index than no insurance. But go with me on this. Right now, let's just say we have a two-tailed test. And I'm going to create a variable, and I'm going to call that variable diff. I'm calling it diff for difference. That's kind of a standard thing we do. So let's let diff be mean 1 minus mean 2. All right? So we're creating this variable called diff, right? And we want to create a null hypothesis that says that diff is equal to 0. Well, let's think about what would be the interpretation if diff is equal to 0. Well, then mean 1 would be equal to mean 2, right? Which would mean there's no difference. Our means are the same. Let's have an alternate hypothesis that says diff is not equal to 0. That would mean our means are different. So I'm simply trying to determine which hypothesis is going to have support. Is there enough evidence for us to reject that null hypothesis, that they're the same, in favor of the hypothesis saying that they're different? Now, let's create a confidence interval around diff being equal to 0. So let's create a confidence interval around no difference. So that means I'm really creating kind of this margin of error around my null hypothesis, okay? So we're going to start with the null hypothesis being true. You're going to hear me say that in other places. So let's start with diff equaling 0, right? Because if the null hypothesis is true, then our variable diff, which is just the difference in means, would have to be equal to 0. And let's create a confidence interval around that. All right? We know how to do that. We can plug in x bar. Well, if this is a confidence interval around 0, then we're looking at a margin of error around 0. So I'm going to plug in 0 there. And then I have the standard error of 0.04, right? So our confidence interval would be 0, because that would be the null hypothesis is true, plus or minus 1.96 multiplied by our standard error of 0.04. When I do that calculation, I get negative 0.0784 to positive 0.0784. I have a confidence interval. Remember, it's around 0. So if I'm looking at plus or minus around 0, I'm going to have a negative number to a positive number, right? It's going to be symmetric around 0, right? Now remember, our difference that we've just computed in sample means is equal to 0.39. So ask yourself, does that fall in this confidence interval? Right? We're saying, look, for the difference to be 0, we're going to give ourselves just a little wiggle room. Anything between negative 0.0784 to positive 0.0784, well, that's essentially 0. But our difference is 0.39. And don't you agree that falls far outside of the confidence interval, right? It's not in that confidence interval. It's way beyond the confidence interval. Now, I'm a visual person, so I've created this little graphic to help you really see what we're doing. So remember, we're starting with our null hypothesis. Let's let diff be equal to 0. That's why you see 0 in the middle. And we created a confidence interval that went from negative 0.0784 to positive 0.0784. That's our confidence interval. So we're basically saying, look, things don't have to be exactly 0. Well, we're going to just give ourselves a little bit of margin of error. So we have this little bitty margin of error. Anything that falls in that region, look, that kind of supports the null hypothesis, that the difference is really 0. But as we said, our difference is 0.39. It falls way outside, right? It's not even close to fitting into this confidence interval, right? It would be way, if I was thinking of this as a number line, way to the right. So you see my arrow kind of pointing way out into the space. It'd be way over there on the right side. So I know that difference has to be statistically significant because it doesn't fall in the confidence interval for diff equaling 0, right? So I can say, look, we have a statistically significant result in that we have a difference equal to 0.39, and it does not appear to be due to chance. Now, in part 2 of this lecture, we're going to take this a step further because we're going to learn how to conduct a hypothesis test. What we did just a second ago is kind of connected to our hypotheses, but we didn't do a formal hypothesis test. I just wanted to show you how you can interpret a lot of stuff that you're going to see, because research often gives you those means and the standard errors, and you can kind of do your own quick little analysis like I just did and go, oh, that's a significant result. Remember, when we're doing a hypothesis test, we're going to be using our t-distribution. And remember that t-distribution is useful when our numbers, our sample sizes are small, but also remember it converges to the normal distribution starting around 30 observations, right? So if we have a significantly or sufficiently large number of observations, well, our t-distribution and our normal distribution are going to be the same. Also remember, we have to think about our one-tailed and our two-tailed hypotheses and give some thought to which one would be the more appropriate. So that's what we're going to be moving on to in part 2 of this lecture. Please let me know if you have any questions about what we just did, and I'll see you in a few minutes or whenever you have time for part 2 of hypothesis testing, actually conducting the tests. All right, have a great day and thanks for listening.